Okay, so if you're still struggling with completing the square, here is a video to walk us through a couple of types of problems we see when we're trying to write a standard form quadratic expression in vertex form. So with our simplest case, our a value is 1. Remember, our standard form is ax squared plus bx plus c. When this a value, the coefficient of our x squared term, is 1, just like this, we don't have to write it. And our completing the square process is a little easier. So our first step when algebraically representing completing the square is to find the perfect square trinomial that is closest to this perfect square. Now the pieces we've been given are an x squared, 6 negative x's, and I'll put 3 on either side, negative x, negative x, negative x of our area model. Negative x, negative x, negative x. So we can see the dimensions of this are x minus 3, x minus 3. So the nearest perfect square is x minus 3 quantity squared, and that has 9 ones in it, 9 ones. But we have 9 ones. So this blank says we needed 9 ones, we had 9 ones, we can take away what we added in, and the extra or missing is 0. So we have no extra or missing. This came with all the ingredients we needed to make a perfect square. So we can conclude that our original problem was a perfect square trinomial in the first place. Now, when the a value is not 1, things get a little trickier, and we have to be careful with our algebra. So what we're going to do is first factor out the a value from all 3 terms, and that is the process of dividing all the terms by that a value and multiplying it out front. You can't just drop it, otherwise each step is not equal, and all of our steps need to be kept equal. So if I divide 5x squared by 5, I get x squared. If I divide negative 10x by 5, I get negative 2x. If I divide 13 by 5, that doesn't come out evenly, but I can just write it as a fraction or put it in a calculator to find, and I've got lots of fun things in this calculator right now. I can type it into a calculator to find that 13/5 is 2.6. You can choose to work with the fraction or the decimal, but I'm going to show working with the fraction because I think it's easier in the long run when we multiply back in. So you could use the decimal if that is more appealing and you've got a calculator on hand. But now, once we've factored out the 5, we're going to leave it alone. But what we need to do is we need to build that perfect square trinomial by adding in something. And then to keep our expression equal to what it was before, we'll subtract out that same piece we added in. Now, these first 3 terms are the sum of the parts of some area model that can be expressed by the product of the dimensions squared. So if I'm thinking about an x squared and 2 negative x's on either, 1 negative x on either side, I have 2 negative x's total. Then I have a 1 by 1 in the corner. So this is x minus 1 and x minus 1 in dimensions. So we can write, and I keep my 5 out front, we can write this first 3 terms as x minus 1 quantity squared. Now, if I were to actually FOIL out this x minus 1 quantity squared, I get the sum of these 4 parts, which the c term is 1, and that is negative 1 squared. Negative 1 times negative 1. This negative 1 times this negative 1 gives me this positive 1. So what I'm adding in to create this perfect square is 1, but if I add something in, I take it out. Now, I can subtract 1 from 13/5 by remembering that 1 equals 5/5, right? We want a common denominator to be able to subtract, and anything over itself is 1. So I'm doing 13/5 minus 5/5, and we'll see that we have x minus 1 quantity squared plus take away 3, take away 2, so I'm looking at 8/5. And then final step is to multiply our 5 back in. Notice how I use these extra parentheses at every step. Even when I made my perfect square, we started with 2 sets of parentheses so that we remember that the 5 was pulled out of all 3 terms. So the 5 needs to be multiplied by all the terms left. So at the end, we'll multiply that 5 in to the first term and to the second term. And 5 times 8/5 is just 8. 5 over 1 times 8 over 5 has a common factor in top and bottom, and that's just 8. So we have 5 times x minus 1 quantity squared plus 8. All right, looking at the next one, we have negative 3x squared plus 24x minus 12. Now, my first step is to always factor out. And I'm not only factoring out a 3, but I'm factoring out a negative. So I'm dividing each term by negative 3. Negative 3x squared divided by negative 3 is x squared. Positive 24x divided by negative 3 is negative 8x. Notice the sign switches when you factor out a negative. Negative 12 divided by negative 3 is positive 4. Notice that the signs all switched. We had a negative, we have a positive, positive became negative, and negative became positive. And we divided all 3 terms. One of the most common mistakes is just to forget to divide the last 2 and you only take it out of the first, but that doesn't keep our step equal. So we're going to add in something to make a perfect square trinomial, but remember to take that out to find the difference between what we had and what we were looking for. That's our extra or missing piece. So I'm going to make my perfect square, which is always half of the b term. Take your b term, divide it by 2, and that's what goes in your perfect square. And we square it because that's the product of the dimensions. If it's a square and that's the length, x minus 4, and the width, x minus 4, then we multiply them together to make the area. That also means that the bottom right corner of our area model is going to be 4 by 4, 16 units of 16 ones. So the perfect square trinomial or the perfect square x minus 4 squared corresponds to the perfect square trinomial x squared minus 8x plus 16. But we didn't have 16, we had 4. So what's the difference between what we had and what we wanted? That is negative 12. So our final step is to remember that we had 3 of these, right? We completed the square for 3, negative 3 technically, of this single perfect square, or not quite perfect square. We've completed the square. Now we need to multiply that 3 to both terms and redistribute. So we have 3 times x minus 4 quantity squared plus, because a negative times a negative makes a positive, 3 times 12 is 36. So there are 3 examples of completing the square. If you still have questions, please reach out to me or check out the resources posted on Canvas.